A stable V configuration. Two identical uniform beams weighing WB equals 260 newtons each are connected at one end by a frictionless hinge. So that's the hinge at point A. A light, so the weight is not important, horizontal crossbar attached at the midpoints of the beams maintains an angle of 53 degrees, theta 53 degrees, between the beams. So that's the angle between the beams. And since these beams are uniform and they're identical, the center of gravity is right in the middle. So the crossbar is also attached to the midpoints of the beams. The beams are suspended from the ceiling by vertical wires, so there will be tension on these wires, such that they form a V shape. Part A, what force does the crossbar exert on each beam? So the force exerted by this beam at the contact point. Is the crossbar under tension or compression? And part C, what force, magnitude, and direction does the hinge at point A exert on each beam? So on the left beam and on the right beam. So if we look at the forces acting on this set of two beams, we have the tension that is pointing up. This is the tension on the cable. Then we have the weight of the beams, WB. Since these are uniform beams, the center of gravity is right in the middle. So it is at this point, WB is pointing down. There will be a force exerted by the crossbar on these beams. So let's say that this force is pointing to the left. So it's either under tension or compression. If this is under compression, then it applies a force to the left. So that's going to be the reaction force. And another force to the right on the right beam. And there will be forces on the pivot point, which will be balancing these forces. And the theta, the angle between the beams, if I draw a perpendicular here, since these are basically the midpoints, they are identical beams, so this is going to be an isosceles triangle. This angle will be theta over 2, this angle will be theta over 2. So if I draw a perpendicular to this beam here, this is 90 minus theta over 2, and the angle with the horizontal here is theta over 2. And similarly, this angle and this angle are the same. So we will have theta over 2 here, 90 minus theta over 2, 90 theta over 2 here. Okay, so we have identified all the forces acting on this set of two beams, and we also set up our coordinate system x, y, z. So first thing I do is I consider two beams together. Consider the set of two beams. All right. What are the forces acting on the set of two beams? Well, there is the weight that is acting down, and then we have the tension pointing up on the y-axis. So the net force on the y-axis should be equal to 0 because this is equilibrium. It is 2t pointing up, twice the weight, 2wb pointing down. This must be equal to 0. I find that the tension on these wires should be equal to the weight of the beams. Okay, since we see that the tension balances the weight, the forces at the point A, F sub A, must be there to balance the force exerted by the crossbar. So it must balance F. So if I write the net force on the x-axis, for example, if I look at one of the beams, so let me clarify that here. The left beam only, let's say, left beam. If I write sum of the forces on the x direction, it's going to be equal to F pointing to the left, and it must be balanced by the force at the hinge pointing to the right. So I should see that FA is equal to F because the net force on this beam has to be equal to 0. Now, how do I find this force F? If I calculate the torque with respect to this pivot point, point A, that must add up to 0. So if I continue with this left beam here, so I see that there is the weight at a position L over 2, the length of the beam divided by 2, and it's making an angle theta over 2 with respect to the beam. So the perpendicular component of this weight is WB sine theta over 2, pointing in this direction. So it's R cross F. So I see that I go with my 4 fingers of the right hand here towards the, curl them towards the force. The thumb points upwards, indicating that the rotation effect of this force is counterclockwise. So it's a positive torque. So I see that this is L over 2 multiplied with the perpendicular component of the force, WB sine theta over 2, and it is positive. The other force that has a torque effect here is the force F, which is basically in the horizontal direction, making an angle theta over 2 with the normal to the beam. So it's F cosine theta over 2 at a distance L over 2. Now, if I look at R cross F here, I also see that the sense of rotation is also counterclockwise. So this is also a positive torque. So this will be plus L over 2 F cosine theta over 2, the vertical component of the force. The third force that appears here is the tension. And if I look at the perpendicular component of the tension here, since this angle is theta over 2, T sine theta over 2 will be perpendicular at a distance L from the pivot point. And if I look at the sense of rotation for this one, R cross F, using my right hand, 4 fingers point towards the tension, curl them from the pivot point to the point of application of the force, curl them towards tension. The thumb points into the board. The rotation effect is clockwise. So it is a negative torque, minus LT sine theta divided by 2 is equal to 0. These are the forces acting on this beam. Well, there is this contact force at the pivot point, but that has no torque effect because we're taking the torque with respect to this pivot point. So I see that these L's will cancel, and I will be left with WB divided by 2 sine of theta over 2 plus minus WB sine theta over 2 minus WB sine theta over 2. Here I have substituted for tension WB, which I have found from the consideration of 2 sets of beams together. So T is WB. And then I have F over 2 plus F over 2 cosine theta over 2. This must be equal to 0. This gives me the minus WB plus WB over 2 minus WB over 2. So I will find F over 2 cosine of theta over 2 is equal to WB over 2 sine of theta over 2. So these 1 over 2's will cancel here. And I will find that the force F is equal to WB sine theta over 2 over cosine theta over 2, which is tangent theta over 2. That's the force exerted by the crossbar on the left beam. It's pointing to the left. Now if I substitute the numbers, the weight of the beam is WB is equal to 260 newtons. Theta, the angle is 53.0 degrees. That gives me an F of 260 tangent 53 over 2, which is 130 newtons. So that's the force exerted by the crossbar on the left beam. Okay, so it's going to be the same story on the right side. I will have the same force F, but this time pointing to the right, and the force exerted by the pivot point on this beam, on the right beam, will be pointing to the left, so they will be balancing each other. I see that the force that I have calculated here turns out to be positive. So with this convention, since F, the force applied by the crossbar turned out to be positive, the crossbar must be under compression. The crossbar is under compression. Why do I say that? Because I have calculated the force applied by the crossbar on the beam, on the left beam. This implies that the force applied by the beam on the crossbar is equal and opposite in direction, Newton's third law. And the same thing is true for the right beam. The force applied by the crossbar to the beam is pointing to the right. That means the force applied by the beam on the crossbar is pointing to the left, equal and opposite in direction. So this is due to Newton's third law. Action-reaction. Okay, in part C, I want to know the magnitude and direction of the force that is at the hinge at point A. So I see that FA, the force in magnitude, must be equal to F, which is WB tangent theta over 2, because that's the only force that can balance the force exerted by the crossbar to reach equilibrium. This is from part A. So what does that tell me? What is the direction of this force on the left beam? It is horizontally to the, let's see, the force at the pivot point is horizontally to the right on the left beam because it's balancing this force F, which is to the left. So it is horizontally to the right on the left beam, and it is horizontally to the left on the right beam. And these are shown with red and blue in my diagram. And the magnitude of the force at the hinge point is 130 newtons. So I know both the direction and the magnitude, and this proves to me that the crossbar must be under compression. So once again, the force exerted by the crossbar on the left beam is pointing to the left, it is balanced by the force at the pivot point F sub A, the red force pointing to the right. And this is equal in magnitude to F. The force exerted by the crossbar on the right beam is pointing to the right. Therefore, the force that balances this at the pivot point F sub A is pointing to the left, and it's equal in magnitude to F. Alright, so in this problem we considered a stable V configuration which is made of two identical uniform beams where the center of gravity is right in the middle. They have exactly the same mass and same weight, 260 newtons. A light horizontal crossbar, it's a light bar, which means we should neglect the weight of this crossbar. Attached at the midpoints of the beams, maintains an angle theta between the beams. So this is the angle theta between the beams. The beams are suspended from the ceiling by vertical wires, where we will have tension. And we want to know the force the crossbar exerts on the two beams, the force that appears at the hinge point, and whether or not this crossbar is under compression or tension. First thing I did was identify all the forces. There's the tension acting on this set of two beams and the weights pointing down. The center of gravity is right in the middle. And then because these two beams touch each other, there will be contact forces at the pivot point. And there is a force that's in the horizontal direction, either pointing in a direction that's away from the beams or towards the beams, depending on whether this is under compression or tension. Well, you can imagine that this should be under compression, so that the crossbar will be exerting a force trying to pull it away on the left beam, and also pointing in the plus I hat direction on the right beam. Since this angle is theta here, this is an isosceles triangle. These are both L over 2. This angle should be theta over 2 and theta over 2, the same angles here. So I see that this angle should be theta over 2. If I complete this to 90 degrees, this is the normal to the beam. This is 90 minus theta over 2, then the angle with respect to the horizontal again becomes theta over 2. This is theta over 2, this is theta over 2. So the tension makes an angle theta over 2 with respect to the direction of the beam. Okay, having identified all the forces, first thing I did was to isolate the two beams together. Look at the forces acting on the two beams. Well, there's the tension pointing up and the weights pointing down. Those are the only forces on the y-axis, so tension must be balancing the weight of the beams. And on the x-axis, Fa, the force at the pivot point, must be balancing the horizontal force F. If I concentrate on the left beam and I write the net force acting on the x-axis, it is F sub A pointing to the right, F pointing to the left, so that they balance each other. So Fa and F are equal in magnitude. In order to find what F is, I consider T is equal to WB information, and I take the torque with respect to the pivot point, where I note that the torque with respect to for the rotation effect of WB and F, I have a counterclockwise rotation, and for that of the tension, I have clockwise rotation, so that has the opposite sign. So the perpendicular distance, well, the distance between the pivot point and point of application is L over 2 multiplied with perpendicular component of the force, WB sine theta over 2. That's the first torque. And then for the perpendicular component of the force F at the point of application, F cosine theta over 2 multiplied by L over 2. And the perpendicular component of tension is T sine theta over 2 multiplied by L, but in the opposite direction. So substituting for TWB, we can solve for F to be WB tangent theta over 2. If we substitute the numbers, we obtain the numerical result. And the numerical result is positive, which tells us that this convention that I used for F is correct. The force applied by the crossbar turned out to be positive with the convention that I chose, which is telling me that the crossbar is applying a force to the left, which means the beam is applying a force to the right on the crossbar. The left beam is applying a force towards the center of the crossbar, so the crossbar must be under tension compression according to Newton's third law. And what are the forces at the hinge point? Since these forces are balancing F, they are same in magnitude. It is horizontally to the right on the left beam and horizontally to the left on the right beam, so that they balance the forces exerted by the crossbar. So that this leads me to the final answer.